very quick introduction. My name's Steve Willson. I look after products and solutions for Violin memory in Europe. And I don't know how many of you have heard of us. Maybe you've heard of us but don't know what we do. But we specialize in doing all flash arrays, 100% solid-state persistent storage arrays. So you know, you think, well, why is there a guy from a hardware company at a Microsoft event? You know, how does that figure? Well, I guess more than 50% of my time I'm spending now in SQL2014 environments and helping clients make the transition from 2008 to 2012 to 2014. And one of the key benefits of 2014 is there's a bunch of features in 2014 which allow us to exploit new classes of hardware. And if you don't exploit new classes of hardware, then you're really just replacing like for like for like, and that's actually not going to give you the benefits that you could get. So we deliver ultra-dense, ultra-fast, ultra-low latency all-flash solutions, specifically, mainly for two market areas. VDI is a really obvious one. Yeah, lots of users, lots of IOPS. You know, that's a fairly straightforward one. But the vast majority of our customers are running databases. They're running multiple mixed random workloads, and they're trying to get more done with the data they've got. And what we find is as data grows, even the standard queries you're running on data takes longer and longer and longer because you've got ever-growing tables. But also the business is asking for much more. They're asking you to run decision support type queries on operational type systems, and they're trying to work out, do we take a copy of all of our data and put it over here and run it in a data warehouse, or do we actually run the queries directly on the SQL, on the operational systems, and get the results we want without knocking the operational systems over? Okay, and that's a major challenge. So I'm just going to spend 25 minutes today talking about how can you exploit flash memory in a SQL2014 environment, and what does it give you? I think it's a given that flash memory should be faster than some disk drives. I mean, if it isn't, you wouldn't buy it. So it's got to give you something more than just being a bit faster. Okay, so we'll discuss some of those things today. So excuse me as well, I wander around. I couldn't work out how to get the VGA connector working there. So if we look at what's new in 2014, the first one, I guess, the big one, is in-memory tables. Okay, so you can now take a table in a SQL database, and you can actually tag it and say, keep this in memory. Okay, you have to keep the entire table in memory. You can't keep a partition. Yeah, you have to take the whole table and move it in memory. And when that table goes into memory, it's kind of stored in a different format. So on disks, it's pages, yeah? And actually in the buffer pool, it's pages. But in memory, it uses a much more optimized structure. So you move the entire table into memory. And the beauty of that is the stored procedures that are going to operate on that table will also be compiled to use that format and placed in memory also. So you can dramatically speed up. And over the last week, I've been running what we call data immersion events with Microsoft in the UK, and we're rolling out. And we let people try that. You say, look, here's a table, let's move it into memory. And once we've got it in memory, yeah, let's see what the performance differential is. And it's quite dramatic. So if you have a highly, I guess, a highly read-intensive table that's constantly hit for lookups, for references, for searches, it's a great thing to do. So actually, that might be the one that should go in memory. Yeah, stop that hitting the back-end storage. If you move a table into memory, you no longer have a buffer pool copy of the data. By definition, it's in memory. Therefore, there's no value in having it in the buffer pool as well. So it frees up some space there. But the general rule of thumb, if you're going to do this, is you need twice as much real memory, not virtual memory. You need twice as much real memory available as the size of the table. Okay? So if you've got a 10-gig table or a 20-gig table, you need to go find 40 gig of real memory. Yeah? And it also means in a virtual world, you have to make sure you have actually got the real memory reserved, yeah, and not a page version of that. Otherwise, you'll go back to standard performance. So it's a fantastic opportunity to move larger tables or more frequently accessed tables, but you need to go find some memory to do it. As we say, you don't get anything for nothing in this world. So you can have this, but you need to find some more resources. What else is in 2014? So the other one is Columnar Indexes. So this is really for sort of decision support and business warehouse type queries. This is where you're doing intense querying of very large quantities of data. So a columnar index is it's a column-based index rather than a row-based index, and that also sits in memory. Okay, so you can choose for certain large table spaces, yeah, where you're regularly going to go across the entire contents of the data, in a frequent way. You can choose to have the index locked in memory, yeah, the entire index locked in memory in a new format. Okay, that also takes memory, and you need to account for that. The size of the index depends on the type of data and depends which fields are indexed. If it's something really simple, like let's say it's cardinal values for, I don't know, how many cars are insured in this household, for example, yeah? That's really simple, because it's going to be 1, 2, 3, 4, maybe 5. Yeah, but there's only 5 values, and that will really, really compress quite nicely. If it's fuzzy text search indexing, yeah, that's not going to compress at all well, so you'll need vast quantities of memory. So you need to test these things in your applications, yeah? If I had a columnar index, would it make it faster? And B, how much extra memory would I need to achieve that? So these are the 2 big features in 2014 designed to give you in-memory, okay, whatever in-memory means. So it's important when we talk about Flash because we impact the memory elements of what we do. So it doesn't matter whether it's Microsoft or SAP or SAS Analytics, it doesn't matter, they're all talking in-memory this week. Everything's about in-memory, it's the latest buzzword. But the reality is all databases are in-memory databases. So you see in this example here, you've got buffer pools in SQL, which is just a memory allocation for the most recently accessed or the most frequently accessed blocks in a database. And the hot data is held in memory anyway. That's just standard SQL. So it's already an in-memory database. But the cooler data is left back out on disk. It's left outside on disk. And if you need that data, you're going to have to bring it back in. And that's the difference between sort of a few nanoseconds of access time and a few milliseconds of access time. And that's huge. It's a huge difference in time. It's really important, though, the disk copy of the data has a really important, because the disk holds hot and cold data because it is your one and only persistent copy of your database. Yeah? So disk takes a special role, which is when the power's turned off and the database is shut down, your data is still there. That's important. The other thing is transaction logs. Okay? So if you've got a write-intensive or you've got a heavy update process on your database happening overnight, all of the transaction logs must hit persistent media. Yeah? They can't be left in memory. You know, this idea you could just leave it in memory and flush it down later on. You can't. So all transaction logs in SQL always have to go to disk, or whatever that is. And in our case, that's Flash. Yeah? So it's much faster content. So in-memory is not a new idea, but there's now new competition for the limited memory you have available. So a standard server today, x86 Blade server, how much memory? 384 gig is probably a fairly standard type memory footprint. You can certainly go up to a terabyte. You might not be buying the same Blade servers anymore. It might be twice the cost or 3 times the cost. So saving memory is still important because it determines how many servers I deploy, and it determines what I can do with it and how many tables I can put in the memory. So if you think about this, I kind of drew this out this way. If you imagine a database, and the database has a whole series of blocks in it, and some of them are hotter and some of them are cooler, okay? This graph shows, I've ordered them here from the hottest blocks to the coolest blocks, and you end up with a curve. There's a bunch of data that's really hot, and then it very quickly tails off into very cool data. And really what your buffer pool is designed to do in a SQL database, and the reason you size it, you're trying to get 80 or 90% of the hot blocks to stay in memory. That's how you size that chunk of memory. So the rest of it will go out to disk. My job is to keep the minimum out to disk. Yeah, the coolest stuff should stay out on disk. And that's how we determine the size of buffer pools. And by modifying buffer pool sizes, you can see what the impact on storage is. So I'm competing for memory with other processes, and I have a choice to make how much is definitely going on disk and how much is definitely staying in memory. So if you think about a hypervisor environment where you've got multiple copies of an operating system, you've got multiple applications or stored procedures, and then within that your footprint, you've also got a data cache. So each virtual machine in a Hyper-V world also has a data cache, which is the buffer pool. For your server with its 384 gig, yeah, let's say the hypervisor steals, I don't know, 32, 64 gig of that for whatever it does. Each copy of the operating system will need a minimum working set. Your application will need a minimum working set. Sometimes that's based on the number of users or number of threads. There's a relatively small proportion of memory left for holding data, stopping you accessing disks. So my job as a guy that sells solutions based around Flash is how can I maximize the utilization of the DRAM footprint in the server, which is by definition the fastest and the most effective solution for getting data processed, and how can I help it speed up the application? So, very simple model here on CPUs. So we've talked about memory, and memory is a constrained resource, and we'll talk about that in a minute. Compute resource. In a very simple computing world, when I'm in CPU mode, I'm doing some real work, my application's doing something useful, and then I probably either have to write some data out or I have to ask for some data to come back in, before I can carry on with my processing. So the red block here is I'm waiting for some data to come from something inordinately slow, milliseconds away, not nanoseconds away. It's because it's on disk, it's somewhere else. We do assessments every day for whether it's SQL or Oracle or Ingress or whatever we're working on. And it's very, very typical that we go to either small but sometimes very large clients who we kind of expected to have solved these problems already. And we look through the database logs or performance statistics, and we find that 50, 60, 70% of all the processor time is actually doing nothing but waiting. It's just sitting there waiting, doing nothing. And from a cost point of view, so you've bought a server, you've put it in a rack, you've given it some power, you've given it some cooling, you've licensed it, which is probably more expensive than the server, and then 60% of its time is doing nothing. Nothing useful for you at all. And because it's slow and it's not performing, you try not to add too many more applications to the same server, so you buy another server and buy another server and you buy another server, because Project A wants its own server and he's not going to share it with Project B and all that stuff. So you end up with lots and lots of servers at relatively low utilization levels. And what this graph at the bottom shows is that while it's waiting, so the natural shape of that application demand would have been like this, but it's been flattened because I'm waiting for I/O, and while I'm waiting for I/O, I can't really do any more useful work. So our job is to solve this problem, because if I solve this problem, I could potentially halve the number of servers in the environment, delivering a better service footprint. So what happens if I put a low latency material like Flash in? So Flash, there's different varieties of Flash storage. If you imagine a good working SAN disk delivering you a 5 millisecond response time, I typically deliver a 500 microsecond response time. Okay, so it's an order of magnitude smaller, probably 10, sometimes 20 times smaller. If I can remove that wait time so I can actually do more useful work, I get better value from my server, and I complete the job far faster, whatever that job is, whether it's a query or a batch update, I can get that done. Okay? But the most important thing is, if I'm virtualizing it or if I'm consolidating the database instances, I can then start stacking workloads on top of each other, because there's no longer any contention, I'm no longer waiting for I/O. I can start stacking workloads on top of each other, and I can drive the utilization of the server up to something useful. So when I'm planning SQL farms or database as a service farm, I want to get as many databases onto the platform as possible, each of them performing brilliantly. And that's really what Flash lets you do, is deliver many more workloads on that. Okay, so we've talked about CPU efficiency, we've talked about memory efficiency. Today, we've got the buffer pool, which is a proportion of memory, which you define, and everything else is on disk. How can Flash change that? I mean, how can Flash impact my memory utilization? Well, let's assume that I'm not going to be given any more memory, but I do want to exploit some of these new features. So I do want some in-memory tables, I do want some columnar indexes. I'm going to have to find some space in memory to do that. So what we do is we say, okay, the only thing we can really shrink to make this happen is the buffer pool. That's the only other thing we have control over in terms of memory allocation from a database. So if I shrink the buffer pool and give some of that buffer pool memory over to in-memory and columnar tables, and I change the storage model from being a relatively slow millisecond disk-based solution to a relatively fast microsecond-based solution, Flash, can I make up for the smaller buffer pool by having a faster response time? Because I'm forcing you to go out to storage more often than you were, because I've taken some memory from you. But if the storage is far, far faster, maybe I'll get the same performance, maybe I'll get the better performance, but more importantly, for the tables that need memory, they're guaranteed to get that slot. So this is a test that we ran last week. We did it with Microsoft and a UK-based Microsoft partner. We took a workload which simulates a web application, and the web application simply, it's a bit like a basket lookup. So it does a search of a retail website, it looks for a number of items that meet a criteria, and then it goes into some of those items and looks for detail. So it's a fairly common sort of query type update. And we did 3 different tests, and the reason we ran them 12 times was for 2 reasons. One is to make sure they're consistent. It's the same test run 12 times. And the other thing was to make sure that the storage array, the Flash storage array, our storage array, was being used for something else, and we needed to make sure that the other thing that was going on the array didn't impact the response times. And as you can see here, it's consistent. There was other workloads running on this. So, it's minutes up the side. This sequence of accesses or simulated accesses to a SQL database took about 3 minutes, 20 seconds if we left it on enterprise class storage. So just running the sequence of threads against the storage, it will take about 3 minutes 20 to finish what we were doing. So once we'd run it once, and we deliberately put too much buffer pool in, and we knew the size of the data set, the second time we run it, we knew that all of the data access were going to come from DRAM. Yeah, they were never going to go outside for a data access again, because we'd warmed up the cache, and the cache was fine. So the red bar there this is the performance you would get in a nirvana situation. This is all coming from DRAM. This is as fast as you're going to get it. Okay, and you can see the difference. The third test is flush the cache again, yeah, but move the data to an all-flash array, yeah, and see what the difference is. So how much slower is an all-flash array versus having it ready in memory? And you can see there, it's about 9%, okay? So the cost in slowing down the application by squeezing the memory footprint down to 0 in this case and putting it back outside onto flash was 9%. Now, it's a 9% cost, but compared with going out to disk, yeah, it's still phenomenally faster. So the point here was we'd artificially squeezed the buffer pool to 0 by flushing it, yeah, and we'd run exactly the same workload. So Flash brings us two things. Flash will allow me to put many, many more applications on the same physical CPU. That's okay, but if I don't have any more memory, yeah, I can't consolidate these anyway. If I can halve the memory footprint as well by forcing it out to Flash, I now have a model for driving new Microsoft features on the same server footprint I've got at faster performance, but double the density. And that's really what Flash offers. Flash is, you know, for developers or for SQL experts, storage and infrastructure is really dull. Yeah, it just is. Yeah, but if it lets you do more of the things you want to do with your business application, then we can do it. So Flash saves memory and Flash exploits CPU. Okay, so how do we deliver that in a Microsoft world? We have different solutions for different environments. So one thing we've jointly developed with Microsoft over the last year, and it's been out for about 3 months, and we're just doing the first installations, I guess, over the next week or so. We've taken our all-flash array, and if you want to learn more about how we do all-flash very differently to everyone else, because we don't use SSDs, yeah, we use memory boards to do it. I can talk to you upstairs or over lunch, but that device there has 70 terabytes of flash in an appliance that's 3U. Sorry, wherever I'm standing, it's making a horrible noise. I have 70 terabytes, that's 44 terabytes usable, ready for application space, but I deliver it using Windows. So embedded within this system, we have a two-node Windows 2012 R2 cluster, a tightly coupled cluster, and all of the memory in there is actually PCIe attached for low latency. And what we do is, we've worked with Microsoft, so every single copy of 2012 R2 has a kernel change in it that spots Violin arrays and does something different. Yeah, it manages data differently in a Violin world. So in your environment, this would sit in your environment. You'd manage it just like any other two-node cluster. You would deliver SMB folders, yeah, directly to the application servers, however you need to do that, and we deliver it over 10 gig into Ethernet. We use another technology called RDMA, which is relatively new, which is a memory-to-memory transfer. So from your SQL client, your SQL Server client, to the storage is a memory-to-memory transfer, unlike Fibre Channel, where your server's having to control that conversation. This is a memory-to-memory. So we have an environment here where I could put 70 terabytes of all-flash on the floor, I could carve it up as folders, and I could deliver it out to SQL servers, and then you can use it either to store data. We're doing some testing at the moment to see if we can use it for buffer pool extension as well, yeah, increase the size of the buffer pool. But we're into situations where we've got clients in Denmark, for example, where they've replaced their storage with a Violin Windows Flash array, and their batch jobs are 31 times faster. Yeah, so instead of pressing the limits of midnight to 7 in the morning to get your batch jobs ready for the next working day, 31 times faster, which means the backup's always complete, which means that the data cleansing and data integrity check's always complete. So it's an operational change as well. So in terms of cost reduction, one of the issues that people are dealing with at the moment is moving from core-based licensing to socket-based licensing. Yeah? And if you don't do anything, there's a fairly steady uplift in the cost that you'd pay for software assurance. But in this world, I've made their servers far more efficient, so I've cut the server footprint, the core footprint's gone down. And as you can see from the middle graph here, they were going to have to go to that cost in the middle, yeah, by just transitioning from 2008 to 2012. But by consolidating the servers, I've cut the cost down dramatically. There's also a data center saving as well. So there's a cost implication here as well by consolidating. And if you're going to make that move to 2014, cost is a key consideration, because if you could just license half the servers I license today, that's probably far more palatable. So, I guess in summary, we've got significant new features in 2014, but to exploit them, you need some more memory. Yeah? If you don't have more memory, you're going to struggle to exploit them. Memory is a really scarce resource. Yeah? It's the most scarce resource, and it's also the most effective way of delivering data to processing. Most CPUs are underutilized, so if I want to consolidate servers or consolidate database images, I still need to solve the memory problem. Flash kind of gives you back half your memory and lets you not worry too much about coming out to Flash. Okay, but it also can be delivered in a method that, I guess, in a Microsoft environment is far more familiar. It's an SMB folder. So I could put an all-flash array in, and I could deliver, if I wanted to 40 of my biggest database servers. I could deliver them each with 1 terabyte folder, okay, which will operate at microsecond latency. Okay, so it's like putting a flash card in every single server, but not having to put a flash card in every single server. Okay. Managing it in a high availability way, in a shared high availability way, so you can move the folders around from use case to use case, or change the size of it depending on the needs of the different servers. Okay. So thank you very much for your time. That's a broad overview of what we do. If you'd like any more information, please come and see us upstairs and let us know how we can help you. Thank you very much.